So what I'm going to do today is we're going to start with pH, sort of the intro lecture to pH, and then we're going to go back to this at the end of the lecture. Okay? Now, this is the third of a series that I think are really important. You've heard me, we've already talked about the texture mineralogy. We just got done with organic matter. The last of the really important, I mean, not that the rest of the semester isn't important too, but from my perspective, the three most important series of lectures are organic matter, texture pH, and then this one, which is, let's try this again. Organic matter, texture mineralogy, and then this one, which is pH. Okay, so to start talking about pH, we're gonna sort of, what is pH? And then we're gonna sort of relate it to what soils are. And then what we're gonna be doing from there is then we're gonna start talking about the processes that actually produce pH. What are the, and that's what basically today's lecture is all about. Okay, we're gonna get you guys up to speed as to what pH is. We're going to relate that, why pH is important to soil, and then we're going to talk about what are the processes that in fact produce protons and hydroxide. What are the things that produce these pHs? Okay? So this could easily just say acidity. It doesn't necessarily have to say soil acidity. Okay? But we're going to be talking about soils. So what in fact is acidity? Well, it turns out that water disassociates. Okay? And it disassociates at a constant. Okay? Water basically disassociates into protons and hydroxide. If you can put these two together, it's going to be water. But it disassociates at a constant at 10 to the minus 14th. That means 1 out of every 10 to the 14th water molecules in a glass of water is disassociated. Okay? Now, both of these are present, but they are in fact disassociated. Now, the measure of pH is a measurement of the concentration of the proton. There is also something called pOH. Has anybody heard that one? Okay. Basically, that's the concentration of hydroxide. But interestingly enough, if you know the concentration of this, you know the concentration of that. And I'll talk about that in a moment. Okay. So basically, about 1 in 10 million water molecules are disassociated at a given moment. Okay, now these water molecules will reassociate, but another water molecule will dissociate. So it's at this constant of 10 to the 14th. Therefore, the ion product of this dissociation is a constant at that 25 degrees Celsius, and that's that constant. Okay? Now, this number here, if you think about it, and remember we're talking about pH, this number here should mean something. What's the scale of pH? 14, up to 14, 0 to 14. Okay. Therefore, when water is pure, this dissociation is equal. There's going to be an equal part of protons to hydroxide. Okay, so this dissociation right here of protons to hydroxide are going to be the same. So the concentration of protons is going to be 10 to the negative 7th. The concentration of hydroxide is going to be 10 to the negative 7th. When you multiply the two of them together, you get that constant of 10 to the minus 14th. Right? Does that make sense to everybody? Now, the reality is, though, in the real world, these concentrations of hydroxide to protons can change. They can flip. Okay? So as the proton concentration increases, the pHs go down, the hydroxide concentration decreases. Okay? This is a constant. So as the concentration of this goes down, I have an increasing concentration of protons. As I have a decreasing concentration of protons, I'll result in an increasing concentration of hydroxide. They're always in balance to that constant. Does that make sense? Now, one little caveat. The reality is we can, in fact, blow past this constant. We can make things that are more acidic than 1. We can do it in the lab. And in fact, we often do it when we have acid mine waste. But this is where the scale comes from. One way to take a look at this is what's straight out of your book. This is the concentration. Okay, so here's the constant negative 10, but this is how many zeros we're looking at from the decimal point. Okay, this is pH. Okay, as the pH increases, the concentration of protons is going down, which means the concentration of hydroxide is going up. Does that make sense? When you get to the pH of 7, they're at equal concentration, 10 to the minus 7th. Cool beans? Questions? Pretty straightforward. Now, how do we actually get to the pH scale of 1 to 14? Basically, we take that constant, whatever it is, and we apply the negative log to it so that it's an easier number to look at, in essence. Okay, so if the concentration of the protons is 10 to the minus 6, the pH is 6, because what we do is we take this concentration and we apply the negative log to it and we turn it into the pH of 6. Right? So if the pOH is 10 to the minus 8, minus 8 plus minus 6 makes the minus 14. The pOH is 8. Does that make sense to everybody? That's how we get the conversion to the pH scale of 1 to 14 versus saying it's 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. Does that make sense? Okay. Finally, we're almost there, guys. Finally, as the ion concentration is always maintained at this constant, at a pH of 5, my proton concentration is going to be negative 10, my hydroxide concentration is going to be negative 9, and my total constant is 10 to the minus 14th. So at a pH of 5, my pOH is 9. So 5 plus 9 is 14, right? We can do the same thing here. At a pH of 8, my proton concentration is 10 to the minus 8. My hydroxide concentration is 10 to the minus 6. Gives me a concentration of 10 to the minus 14th. That constant, pH of 8, pOH of 6. Make sense? Cool beans? So as a result, if you know the pH, you know what the concentration of hydroxide is. Because I know what the concentration of the acid is, the protons, and I know it's at a constant of negative 14. Therefore, I just add it to the 14, or subtract it to get what the pOH is. Cool? Take a deep breath. You guys survived it. All right. Let's give you some idea about what this actually means in the real world. This is straight out of your book. Okay, and what I did was I basically took some of these and added some other ones. But basically, this term is very strongly alkaline, neutral. And I gave you some ideas about what things are at that pH. So neutral pHs, basically 6.6 to 7.3. You're looking at things like saliva, blood, shrimp. Hey, come on, it was cool. You had to throw it in there. All right, at the extremely acid end, you're looking at less than 4.5. You're looking at things like vinegar, stomach acid, soda. Okay, very strongly acidic, 4.5 to 5. You're looking at beer, tomatoes. Okay, as you move your way down through this system, you get to moderately alkaline, 7.8 to 8.4. You're looking at seawater, sodium bicarbonate. Okay, this is one of the reasons why we take sodium bicarbonate to settle our stomachs. When our stomachs, we have an acid reflux or something like that. We throw this in, it neutralizes the acid that's in our stomach, brings it back down to more neutral. Okay, not that our stomachs are not acidic as they are already. Okay, very strongly we start getting in, or strongly we start getting into borax, 8.5 to 9, and very strongly we're talking about milk of magnesia, ammonium, and lime. Okay, just to give you some ballparks, these are terms, things that you guys all know, right? Is anything in there that's unfamiliar? Lemon juice, I mean, eggs, 7.6 to 7.8. Okay, cool? Okay, so that's the pH. Now, let's talk about where this stuff is. Now, the assumption, I mean, generally when people start talking about pH, they generally start thinking about, well, you know, where is that acidity and, you know, what's going on? Well, if you look at the landscape of the planet, red basically means acidic, yellow basically means neutral, blue basically means basic. Okay? And you can see that as you move across the planet, there's a lot of distribution of acidity, or pH, across this space. Now the question then is, well, what's controlling this? Why is this acid and this is alkaline? Now it has huge consequences on things like agriculture and engineering and water quality and things like that. But let's take the step back and say, why is it in fact acidic? What's going on? Okay? And that basically is what we're going to be talking about the rest of this lecture. Okay? Now, I want to throw a slide in here. Oh, you know what? Let me throw this slide in here first. Okay. You look at a slide like this, you look at a picture like this, and the automatic assumption is, well, everything in this zone here is going to be really acidic. Okay? And everything in this zone right here is going to be really alkaline. But the truth is, if you take a look at an individual location, and we're going to take a look at a location right in here in Indiana. Okay? Now this is the results of pH testing, and I don't remember what year this is, but this is basically a crop consulting company in Illinois. Okay? And what they've done is they've taken a look at all of their soil samples that have come in over a year, and they basically plotted out the pHs. Now, granted, this company could be getting soil samples from China. It could be getting them from Indonesia, wherever. But in all likelihood, most of the samples that they're getting are probably fairly local to Indiana or Illinois. Okay? The important point that I'm trying to make here is, while we have maps like this that sort of talk about the pH distribution across the entire planet, the reality is when you start getting into an individual location, the pHs of this state tend to be around here. But the reality is they bracket a rather large range. Okay? So just because you're in Central Africa right here doesn't mean all of the soils are going to be at 5.3. They're going to be bracketing a larger range of pHs. Okay? Does that make sense? That's sort of the take-home point of this slide. All right. Now, today's lecture is all about, the rest of this lecture is all about how we get the acidity. But I want to talk about, just a segue, why this is important. Okay? Now, this is a slide we're going to talk about. We're going to see this slide later on. Okay? This slide, and let's talk about the slide first. This picture right here represents the colloid, some sort of colloid. Now, this could be an organic colloid or clay colloid. Okay? And the surfaces of this are basically those, this is a charged particle. So there is a certain amount of cation exchange capacity associated with this particle, right? Okay. Now, around this particle is the soil solution. And there's a certain amount of ions that are in this soil solution. Okay. Now, those ions are going to be reacting with this cation exchange capacity associated with the colloid, right? Now, as the solution, the concentrations in the solution change, the ions that are going to be associated with this cation exchange capacity, are going to change. Does that make sense? So as I start changing the proton concentration, as I start changing the acidity, I'm going to start changing the ion concentration in the soil solution, which is going to result in exchanges in the cation exchange capacity of the bases that are actually held on to the cation exchange capacity. Okay? This is why acidity is so important. What do you imagine? Just think this in your head. As the pH of this soil solution starts going down, what does that mean? It means the concentration of protons in that soil solution are going to start going up, right? Okay. What's going to happen to the protons that are in this soil solution? Some of them are certainly going to be leached out of the system. But what are some of them going to do? They're going to start exchanging with the bases that are on the cation exchange sites, which means those bases are going to go into solution. What's going to happen to them? Some of them potentially will be taken up by plants, but much of them are going to be lost to the system. And what's going to happen to my reserve of bases that are on these cation exchange sites? I'm going to start losing them. So the consequence of the acidity going into this soil solution has huge implications for the nutrients of your soils. Does that make sense? Questions? No? All right. So let's take the next step. What is it that controls this pH? Where does the pH come from? And it's basically broken up into 8 different things. The first one is carbonic acid. Okay, that's the rainwater, and we'll talk about each one of these. The second one is biological metabolism. Organisms just doing what they do. The next one is the accumulation of that organic material. Fourth one is oxidation reactions, and I'm going to talk about two in particular, sulfur and nitrogen. Okay, the next one is acid rain. Next one is plant uptake of cations. Next one is aluminum. And the last one is the parent material, or I should say disillusionment, the weathering of that parent material. Okay, good? Let's start with the first one, carbonic acid. Chemical reaction, not a big deal. Basically what we're looking at here is we're looking at an organic molecule in the presence of oxygen. It's decomposing, it's being decomposed, we're respiring, okay? And in the presence of oxygen, the byproduct is CO2 and water, okay? CO2 is abundant in the atmosphere, and every time it rains, there's water, okay? There's actually humidity in that air as well, even when it doesn't rain, okay? It turns out that CO2 and water can combine. They react together, okay? That reaction is basically CO2 and water, and what it does is it creates a very weak acid. It's carbonic acid. Rainwater is naturally acidic. Okay, forget about acid rain. Because of the presence of CO2 in the atmosphere, when it rains, that water is going to react with the CO2 and it's going to make an acid, carbonic acid. Okay, that acid is fairly weak. The pHs are ranging from 5.5 to 6-ish, maybe 6.5, okay, 6.3, okay, but it's a weak acid. And it goes back to my story, you know, I say this all the time, you give me a weak acid in a million years, I'll weather away everything. Well, this is a really weak acid. The base does not completely dissociate. It only produces one proton for two potentials, okay? But this is a proton. It rains, where's that proton going to go? The soil solution, right? So it's putting protons into the soil, which means it's going to be changing the pH of the soil. Question?
On the slides online, it says pH is ranging at 6.5, and there.
That's an older slide, sorry.
This is wrong.
Yeah, this is correct. Okay, the next one, biological metabolism. You start eating something, there's other byproducts besides CO2 and water. We are not totally 100% efficient. There's waste products. And some of those waste products, here's that organic molecule again in the presence of water, of oxygen and water. One of those byproducts is basically organic acids. These are fairly strong, okay? Their pHs are ranging from around 3.5, a much stronger acid than the carbonic acid. Okay, what's going to happen when the microorganisms start decomposing, or the worms start decomposing, or the termites start decomposing organic material in the soil? This stuff is going to go into solution, and I've now added another proton to my solution. I'm acidifying my soil. Make sense? Okay. Questions on this one?
Yeah, is it always a hydroxyl group?
Is it always hydroxyl group? I don't know the answer to that one. I think it predominantly is because of the issue of the organic material. I suspect, there's other types of acids that come out of byproducts, though. Urea, there's some more simple ones, but yeah, predominantly. I'll check up on that one, though. We certainly have the hemic and fulvic acids, but those are the same. They're coming off these carboxylics as well. So, all right. The next one is actually the accumulation of organic matter. Now, this is a two-step process, but you have to sort of think about this. And this actually goes back to that slide that I had with the colloids in the soil solution. Okay. First is you start putting this organic molecules into the soil. And remember I was talking about pH-dependent charge and all that kind of stuff? Well, this is a charged molecule. Okay, and if it's a charged molecule, what is it going to be doing? It's going to be attracted to anions and cations. Now, if it happens to be attractive to cations, base cations, and it starts pulling out bases from the soil solution, what's going to happen to the relative concentration of protons in that solution? Okay, so think about this. Now, let me draw this on the board. Here's my soil solution. Okay, and in this soil solution, I have a relative concentration of protons to bases. Okay? Does that make sense? Now, the pH is dependent upon this. concentration in the entire soil solution. So what's going to happen if I start collectively pulling these out of the soil solution and leaving this behind? The relative concentration of this is going to do what? Right? So what is that going to do to the pH? It's going to increase the protons, which means it's going to lower the pH, right? Now, this is a two-step reaction. The first part of it is this complexation. And when I start changing the pH, I'm also going to remember pH-dependent charge. As I start lowering the pH, what's going to happen to the colloid charge here? Remember pH-dependent charge. OK, let's start with the easy one. OK, if the pH starts to raise, what's going to happen to those charges? Here, right here. Imagine this is the line right here. As the pH starts to raise, I'm going to have more hydroxide in the soil solution, right? What's going to happen? They're going to pull this proton off and make water, and it's going to make this relatively much more negatively charged, right? Which means this molecule at first is going to start pulling in more base cations. Okay, now if I start pulling in more base cations and I start increasing the relative concentration of the protons, what's going to happen to the pH? The pH is going to start dropping, right? And if the pH starts dropping, let's go right back to this. If the pH starts dropping, what are those protons going to do? They're actually going to go back, and then another proton is going to bind on here, so I in fact have two, and I now have a positive charge, right? Now what's going to happen to those bases that are here? They're going to go back into solution, but what's going to happen to them? If they don't get taken up by the plant, they get leached away, and so I've lost the proton. Because of this change in proton concentration, I've lost my bases. Does that make sense? So it's going both ways. Okay, I got a couple no's. It doesn't make sense. Let's keep this here. Okay, here's my oxygen. Here's the edge, right? And I got a proton associated with it, right? What's going to happen when the pH starts going up? Okay, if the pH goes up, my proton concentration is going to go down, but my hydroxide concentration is going to go up. Right? Make sense? Hold on, Lily. Does that make sense? If this starts going up, what's going to happen to that proton? It's going to get pulled away, and it's going to combine with this hydroxide to make water. Right? So as a result, what's going to happen to the charge here? It's going to become more negative. Make sense? Okay. Now, if it becomes more negative, what's going to happen to these bases that are in solution? They're going to start binding. So we now have cation. We've increased the cation exchange capacity, right? Now, you got to realize that more protons are coming into the system. Every time it rains, more protons. But there's a limited amount of bases. So I start pulling these protons these bases out of solution. This relative concentration is going to increase, and I'm getting more every time it rains. So what's going to happen? Those protons are going to start bouncing off these cations, right? And as a result, my pH is going to start going down, which means my hydroxide concentration is going to go up. My proton concentration is going to go up. My hydroxide concentration is going to go down. This is going to become a positive charge. The bases are going off into solution. Where are they going to go? Some of them are going to get potentially caught by plants. Much of them are going to be leached from the system, which increases the loss of my bases. Does that make sense? Now, this is all happening at the same time. Okay? Yes? Questions? Go.
Was that proton on the left there attached to that O? Or is that just
This proton was attached to the O initially.
so what's happening with the O now?
Well, this proton basically got turned into water. So this now became a negative charge, okay, which means a base, some sort of base attached to it. I think the take-home message of this is that what's happening here is, okay, if you have, this is part of the molecule, right? This is part of that organic molecule, okay? As the pH changes, okay, the pH, the charge associated with this organic molecule is also going to change, okay? But think about it this way. If it's already, this is a negative charge already, okay? The bases are going to be reacting with this, okay? And they're going to be changing the relative concentration of the protons in the solution because I'm pulling these away, therefore the proton concentration is going to increase. Does that make sense? Okay, now if that's happening, what I'm going to get is I'm going to get sort of a two-prong phase here. First is the bases are going to bind with the colloids. Okay, and what's going to happen is I'm removing them from solution or leaching, which increases this proton concentration. Okay? The organic matter has lots of these hydroxyls, which are then going to change because of the proton concentration, which then is going to release even more bases and, in essence, increase the proton concentration. So it's a sort of a two-prong attack where in both scenarios, you're getting an increase in proton concentration. Does that make sense? Okay? All right. The next reactions are basically oxidation reactions. And there's two of them that I want to talk about. One is sulfurification and one is nitrification. Sulfurification, so this is basically a sulfide versus a sulfite. Okay? In essence, this is a reduced sulfur. Okay? It was used as an electron acceptor in an anaerobic system. Okay? Here's that material. If this material gets exposed to the surface where there is oxygen and water, this is going to be oxidized. Okay? And in the process of the oxidation, it's going to basically make sulfuric acid, H2SO4. This is a strong acid. The protons are going to completely dissociate. And as a result, I'm going to be acidifying the situation. Now, this is typically associated with dredge materials. If you take estuarine materials and you bring it up and dump it on the surface because you're dredging out a soil or dredging out a channel or something like that, okay, those sulfides are going to be in that material. It gets exposed to the oxygen, and as a result, I'm going to acidify the material. When this material comes up from the bottom, high pHs, 8s, 9s, sometimes 10s. Okay? But you expose it, and after a couple weeks, the pHs start dropping, actually faster than a couple weeks, and you get pHs 4s, 3s. Now, this is also associated, what I said right here is this is the dredge material, but this is also acid mine waste, acid mine spoil. This is why all those streams in basically West Virginia and Western Virginia and Maryland are all acidic. Okay? Now, another example of this is nitrification. Now, this has to do more with agriculture, but if I start adding ammonium as a fertilizer to my soils in the presence of oxygen, I'm basically going to be making water and nitric acid, another strong acid. I got two protons for the nitrate. Okay? This reaction is associated with the soils that have a lot of fertilizer. So by fertilizing with ammonium, I am, in essence, going to be lowering my pH in my soils. Now, this might be intentional. You might actually have soils that have a really high pH, and I'm going to add it in this form rather than adding my fertilizer in this form because I want to lower the pHs. But if you're using it, it's going to happen. Okay? It's a simple oxidation reaction. The next one is acid rain. Okay? And this is the stuff that comes from combustion products, but there's also some natural sources. But basically what we're looking at is we're looking at nitrogen and sulfur gases reacting in the atmosphere with the water and making either sulfuric acid or nitric acid. Okay? Again, these are both strong acids. So I'm going to have complete dissociation. Now, rainwater is acidic. That's the carbonic reaction already. But that acidity is nothing like this. This is strong acid. This is a really strong acid. And so as a result, I'm now, when this water hits the ground, I'm now acidifying my soils. Make sense? Another source of these protons. I threw this in here just so you can have an idea. These are pHs, soil pHs, and the darker the pH, the darker the scale, the darker the color, the lower the pH. And if you think about where most of our stack emissions are from power plants in the United States, huge concentration sort of sitting in here. Downwind is where all that SOx and NOx goes up into the atmosphere and gets mixed into the soil water, the atmosphere, and basically comes down. And you can see this transect basically following the wind pattern, moving right up from that Ohio Valley straight up into the northeast. And that's acid rain. Okay? Questions on this one? No? Fairly good? All right. The next one is plant uptake. And this is one that most of us haven't ever thought about before. But what we got here is we're looking at a plant, and the plant needs to be able to bring in to its cells, it needs to be able to bring in things. Okay? Nutrients. Okay? And here's my root. Okay? And here's my cell walls in essence. So this is basically, imagine this is as a root cell. Okay? Now, for that root cell to be able to get ammonium in, because this is the nutrient, it needs to be able to maintain a charge balance. Okay, remember that issue of salts, the solute potential? We also need to maintain this charge. Okay, and so if a positive charge is coming in, a positive charge needs to go out. Okay, and plants have what they call proton pumps. And they literally, the proton powers this pump. The proton goes out, and in the process, it brings a charge in. In this case, it's an ammonium. Okay, if I bring in 2 charges with calcium, for example, I need to pump out 2. Now, I also can use a positive charge and a negative charge to bring it in, but I need to be able to maintain that charge. And the obvious one that they use a lot of is these protons. Okay, now, if they are bringing bases into the soil solution, from the soil solution into the root material, and they're putting a proton out of the soil material into the soil solution, what are they going to be doing to this ratio? What are they going to be doing to this ratio? They're going to be increasing this, and they're going to be taking this out. And so as a result, the soil solution's ratio of protons to bases is going to be increasing. What is that going to mean to the soil pH? It's going to be lowering the pH. Make sense? Okay. Aluminum is another one. Now, aluminum is a positively charged ion. Okay, we don't think of it as a base cation. We think of it as a cation, but it's not a base cation. Okay, do you guys remember what base cations are? Base cations are not true bases, but because of their distribution, they basically act to neutralize protons. So as a result, we call them base cations. Aluminum, on the other hand, does not tend to neutralize protons. In fact, it tends to activate them. Okay? And let's actually talk about how that happens. Okay? Well, aluminum is a fairly large ion, right? Fairly large, and it's also positively charged +3, so it's a large ion, and it has a high charge. Do you guys remember the cation exchange rules? It was mass, charge, size, and complementary. Okay? Well, this one's big, and it has a high charge, which means in all likelihood it's not going to have any problems knocking things off of the colloids. It's going to sit there. Okay? And if it does that, it potentially is going to react with these protons that are in soil solution, creating a hydroxides here, putting the aluminum into the soil solution. Okay? Does that make sense? All right. Now, theoretically, that's going to reduce these protons. But when that aluminum goes into solution, it's going to react with water. It's basically going to hydrolyze it. The proton is going to go into solution, and the hydroxide is going to be pulled out, and it's going to turn into an AlOH4, or AlOH plus 2 or plus 1, depending upon where it is. Okay? Now, this can continue to react. The charge hasn't been balanced yet. It's going to continue to react with another water and make an AlOH2 plus 1 charge. It's still not balanced. It's going to react with another water, creating an AlOH3. Basically, this is a Gibbsite, at which point it's charged. The charge has been balanced. But in the process of moving from this aluminum that came from here In the process of that aluminum balancing out, it has released 1, 2, 3 protons, basically acidifying the reaction, acidifying the soil solution. It's putting this into the soil solution just by it being released. Okay, does that make sense? Question?
If aluminum is so big and highly charged that it bumps cations out a lot, why would it ever be released from the solution?
Goes to that mass action rule. If it doesn't matter how strong you are and how big you are, if you have enough of something else, sooner or later you're going to get knocked off. Does that make sense? Well, it could be being knocked off by the protons. And as that acidity starts dropping, okay, this aluminum is going to go out. Now, by doing that, I've neutralized these 3 aluminums, these 3 protons, because they're now out of the solution. So what's happened is these guys have come out of the solution. And so as a result, I've decreased the proton concentration in the soil solution. So in essence, I've raised the pH. But this aluminum, in turn, is then going to react with the water to create more protons back into solution. So we're depending upon what the pH is of this soil solution. This reaction can go this way, or it could go this way. Okay, it can go this way, or it can go this way. If I have a higher concentration of hydroxide in soil solution, I'm going to be driving this reaction this way. As the concentration of protons increase, I'm going to be driving the reaction this way. Does that make sense? We'll talk about this is a buffering reaction, and we'll talk about this later. Okay? But what's important to remember is this aluminum is going to react with that water. These aluminums are going to react with that water, and if it reacts with the water, depending upon which way it's going to be going, it's either going to be releasing a hydroxide or it's going to be releasing a proton, which is going to be changing the proton concentration, which is going to be changing the pH. Okay? Last one, and this is where we're going to stop here because I've run out of time. Okay, the last one is parent material. Okay, and this is basically the disillusionment of that parent material. And I throw this one in because this is a really good slide. This is New York State. Totally makes sense if you think about it. Okay, these yellow lines here are basically limestone or dolomitic parent materials. Okay, glaciation basically ran this way and rolled through. Okay, now you get down into these zones right in here, you start getting to the shales and sandstones. Tompkins County, ideal location to take a look at this. What's happening to the south part of the Tompkins County versus the north part of Tompkins County? The north part of Tompkins County is close enough to this line that when it got ground through, a lot of the limestone is in the soil. But the southern part of Tompkins County, elevation starts going up, right? The glaciers are leaving the residual material from the limestones behind, and they start rolling over the shales and sandstones. So, pH-wise, the north end of the county has the parent materials that are the dolomites and limestones. The south end, the parent material of the soils, are these shales and sandstones. What does that mean pH-wise? The north end is limestone, high pHs. The south is shales and sandstone, lower pHs. Did you guys see that? What were the pHs of the soils that you saw up at Mount Pleasant? You guys remember? Shale parent material. Acidic soils. What were the pHs of the soils that you got on top of the lake plain when we were at Caldwell Field, when you were doing the mapping exercise? 6s and 7s, right? Versus 5s. Does that sound familiar? Sort of familiar? That had totally to do with parent material. Now, granted, both at the top of Mount Pleasant and at Caldwell Field, they were liming because of the agricultural purposes. But when we got out of those agricultural areas, the soils went right back to their native pHs. And that was due to this versus this. Okay? We feel comfortable with this? Sorry about the interlude. We are going out this today. We're going to go out tomorrow as well, so be prepared for weather-wise. Today is supposed to be nice. Tomorrow it's supposed to be raining, so bear with us. Okay?